So we have observed a few things in those diagrams, right? Let's try to justify. Okay, let's try to mathematically show why it appears like this. Now, when you put a transparent plastic scale or a glass slab, the letters appear to be raised up. Okay, let's see why that happens. Just a moment. You all can note down this formula. We'll be using this. Assume this is a block of glass and outside the glass is air. So clearly there's an interface. Okay, the surface of the glass itself is the interface between air and glass, both of which are media which allow light to pass through them. Suppose there's a particle inside this block of glass. Small particle, okay, point object. Now we know point object, it like reflects light in all directions, or if it's a source of light, it emits light in all directions. So it could either be reflecting or emitting light of its own, but it will emit or reflect in all directions. Now you can visualize some of the rays traveling from that point object through the glass slab and then entering into air. One such ray would be this. See, for some of you, this may seem very easy or well known, but still, these are the basics. We will have to go through them. So suppose there is a ray incident like this. This point becomes a point of incidence. Okay, this is the object. Can one of you tell me what is the angle of incidence for this ray at the interface? What is the angle of incidence of this ray?
0, sir.
0. It is incident along the normal. Angle of incidence is 0. And if I is 0, according to Snell's law, mu1 sin I is equal to mu2 sin R, R will also be 0. So it will continue traveling along the normal itself. So it will enter into air in this direction. Okay. Fine. That is one of the refracted rays from the object, initially traveling through glass, then through air. Consider another ray. Incident may be somewhat like this. Now this ray is about to enter from glass into air. Glass here is the optically denser medium. Optically denser means it has a greater refractive index. Light travels slower in glass, so its refractive index is higher than air. So what is the light going to do here? It is about to enter from a denser medium to a rarer medium. When light enters from denser medium to rarer medium, how does it bend? Towards the normal or away from the normal? Denser to rarer. Isha, when light enters from denser medium to rarer medium, what happens?
So once can you repeat?
When a light ray enters from a denser medium to a rarer medium, how does it bend? Towards the normal or away from the normal?
Away from the normal.
Denser to rarer, it bends away from the normal. So let's first visualize the normal drawn at this point to the glass surface or air glass interface. This gray line is the normal, gray dotted line. And it should bend away from the normal. So instead of traveling in its actual direction, along its actual direction, this ray bends like this. Okay, let me show it bending significantly just for us to visualize. Travels like this. Okay, and in between these two incident rays, there will be infinite other rays. maybe one incident like this traveling this way after refraction, one incident like this and traveling this way after refraction, and so on. Okay, you can consider infinite incident rays. One more like this traveling this way. Fine. So if there's an observer in air trying to look at that object, okay, let's say this is the eye of the observer. Now, where we perceive an object to be present or an image to be formed depends on the point from where the rays appear to be entering into our eye. These rays, if we trace them in the backward direction, okay, I'll remove these extra rays that we have considered. If we trace these rays in the backward direction, or wait, they all appear to be coming from a common point somewhere here. Okay, all these refracted rays appear to be coming from this point. Fine. Just for clarity, let us visualize only two incident rays and two refracted rays. They appear to be coming from the point I. That becomes the image location or the image position for us. Fine. That is the point from which the rays which are actually entering into the observer's eye appear to be coming from that point, capital I. So we will feel as if the object is present at I. We won't be able to see O at all. The original point particle will not be seen by us. What we will see is I only. And this is what happens when you place a transparent scale over some letters. Okay, transparent scale is like a glass slab only. It's a very thin glass slab, of course. The letters are actually on the page. Okay, but light first travels through the scale, plastic scale. You can think of it as a glass. Okay, it's not glass, it's plastic. Light first travels through plastic and then enters into our eyes. Fine. So when that happens, suppose there's a letter written somewhere here in orange color, it appears to be raised up a little. It appears to come closer to the interface when the observer is in air. Okay. We can find out how close it appears to come, how much it appears to rise, we can find out. Just a second. My laptop is not working properly. Never mind. Okay, so if you try to read those letters, they'll appear to be closer to you. Now we know where the object is. Let's assume we know where the object is. Okay, where means we know how far it is from the interface. Let this be the actual distance of the object. Call it as capital D from the interface. And capital D is a magnitude. I'll have to specify that. And we have to find out where the image appears to form. Let's say image appears to form at a distance x from the interface. Okay, x is also a magnitude itself. We have to derive an expression for x in terms of d. And where the image forms depends on how much the light bends, and how much the light bends depends on the refractive indices of the two media. Why did I call glass refractive index as mu1? Because rays coming from the object, that is the incident rays, are in that medium. Refracted rays means rays after bending are in air. So that becomes the second medium. Okay. We'll apply the formula that we just derived, spherical surface refraction formula. Mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R, where R is the radius of curvature of the interface. Rishi, tell me, what is the radius of curvature of a flat interface? How much is the radius of curvature of a flat surface? Pradyun? Infinite. Okay. I don't know why, but many students find this difficult to recollect. See, suppose there is a small circle like this. Its radius will be small. If radius is small, radius is less, curvature is more. Okay. And as the radius increases, curvature decreases. It tends to become like, if you consider a small part of this circle now, it's almost a straight line. Okay. And if the radius becomes infinitely large, very, very large, then you take any small part of it, part of that circle, it will be a straight line. And if it's a sphere, you take a part of the sphere surface, it will be a flat surface. Okay. So a flat surface is considered to be part of an infinitely large spherical surface. Okay. I had given this example in the last class also. Probably some of you were not there. The part of Earth we see around us appears to be flat. Okay, Earth appears flat when we look at it, standing on Earth. But when you go outside and see, you know it's a sphere. Okay, when seen from space, it's a sphere. But the part of Earth that you see, the part of the Earth surface that you see, is a very small part of that sphere, which appears to be flat. Okay, so a flat surface is part of a sphere whose radius tends to infinity. Keep this point in mind. Okay, let's substitute the given values in the spherical surface refraction formula. If r tends to infinity, then the entire right hand side becomes 0. Let it become 0. V stands for image distance, U stands for object distance, and we are supposed to substitute them along with sign convention if you want to use this formula properly. According to sign convention, the direction in which incident rays are traveling is considered positive. So left side of the interface is positive. Anything inside glass is negative. This point P is the pole that we need to consider. Okay. Now object is on the right side of the pole, that is the negative side. Image is also on the negative side. So in the formula, both x and d will be substituted with minus signs. Therefore, it becomes mu2 divided by image distance is minus x minus mu1 divided by object distance is minus d is equal to 0. Send it that side. Mu1 by capital D is equal to mu2 divided by x. Therefore, you get x is equal to d into mu2 by mu1. That's all. That is where the object appears to be when seen by us from this side. So that's the image location. And see, mu2 is that of air and mu1 is that of glass. Here in the example that we have taken, mu2 is air's refractive index, which is the smaller one. Air refractive index is 1. Mu1 is for glass. Glass refractive index is 1.5. Okay. So if mu2 air is less than mu1, then you can say x is equal to, or x will be less than capital D. Because mu2 by mu1 will become less than 1, then x becomes less than capital D. What does this mean? It means image is closer to the interface than the object. Okay. And next case, if mu2 is greater than mu1, what does that mean? Object is in the rarer medium, observer is in the denser medium. Okay, there are chances of that also happening. If mu2 is more than mu1, then x will be greater than capital D. That means image is farther from the interface than the object. Okay. Now, when you place a plastic scale or a glass slab on printed letters, the letters appear closer to you. Why? light first travels through the glass slab, then enters into air. So it is going from a denser medium to a rarer medium, like this case that we have, for which we have drawn the ray diagram. So glass first, then air, or plastic first, then air, means it is going from denser to rarer, mu1 more than mu2. And if mu1 more than mu2, image is closer to the interface than the object. That is why the image, what you see is the image only. You don't see the original letter at all. You only see the raised letter. You only see the image. Okay. And because it is closer to the interface, it appears to be raised. Fine. And you all must have heard of something called apparent depth. The apparent depth formula is also derived based on this itself. We can just rearrange this diagram, rotate this diagram, and get the formula for apparent depth. Let's say there is a flat refracting surface like this. Okay, wait. I think X and D should be there. Let them be there. Positive, negative doesn't matter. We know where the interface is, and we know it's a flat interface, so radius tends to infinity. Okay, there's fine. I can rotate. That's all. This is what this is what you generally see in books where apparent depth of an object is derived. The actual object is O. That is where it is present. Okay. And assume this medium is water. And the observer is outside in air. Okay, you can observe this in daily life also. You take an empty tumbler, keep a bright object inside it. So when the tumbler is empty, you can get an idea of the real distance of the object from your eye. But start filling the tumbler with water. Okay, ensure the object is dense. It should not float on water. It should sink. Okay. Now start filling the tumbler with water. You will feel the object is coming closer to you. That is because you are not seeing the object, you are seeing the image, which is formed closer to the interface than the object. Okay. Fine. So here in this diagram, capital D is the real depth and X is the apparent depth. And what was the relation between them? X is equal to capital D into mu2 by mu1. That's all. You can say that apparent depth is actual depth into mu2 by mu1. Questions based on this are quite common. Fish underwater being seen by a person from outside. Reverse. Person outside or a tree outside or a bird outside being seen by a fish inside. Okay, let's solve problems based on all this. Are the ideas clear? Did you understand how we used the spherical surface refraction formula to derive a relation between object distance and image distance from a flat surface? Isha, is this clear? No response. Rishi,
Yes, sir. It's clear.
Pradyun, did you understand? Okay. First thing to do in optics, in any question of optics, as I say, is to imagine how the rays would travel. Roughly, you can't draw the exact angle of refraction and all, but you can get a rough picture of what is going to happen. Okay, once you visualize that, your answers will be more accurate. Okay. Try this question. One direct application we will discuss. Okay. Assume water is filled till this level. Refractive index of water is 4/3. Refractive index of air is 1. Okay, that need not be mentioned actually. There's actually one more thing we need to be careful about. I'll let you know. Suppose there's an object at the bottom of this tumbler, like a coin. Let's say the height of the tumbler is 20 centimeters maybe. But the height of water in the tumbler is only up to 15 centimeters. There's an observer outside. Let's assume the eye of the observer. Observer is looking at that object or trying to look at that object. The eye of the observer is at a height 40 centimeters from the base of the container, base of the tumbler. Calculate the distance at which the image appears to the observer. Distance from where? Distance from the eye itself. Okay, you have to find out. Try this. What happened? Why is it taking so long? Rishi, any answer?
Sir, 2 more minutes, I'm still following.
Okay, solve it, solve it. Object is in the denser medium water. Observer is in the rarer medium air. So the image will appear closer to the interface. Like you can visualize rays. One ray travels straight like this without bending. Okay, I'm drawing with free hand. Another ray traveling like this bends this way. Third ray traveling like this bends this way. So they all appear to be coming from a common point somewhere here. That is where the image forms. Okay, you have to find out how far that is from the observer's eye. Okay. Pradyun, can you unmute? We'll discuss. If it's not possible, let it be. Okay, Rishi, tell me, how are you trying to solve this?
Sir, so the formula is,
Hmm.
if we substitute it, we get 15 into 4/3.
Which formula are you using? Okay,
Apparent.
apparent depth formula. Okay. Yeah, what you need to find out is also the apparent depth only. But I mean, the answer is not the apparent depth. Okay. You will see it at a distance of apparent depth, but apparent depth and real depth are measured from the interface, not from the observer or from anything anywhere else. They are measured from the interface. The interface here is the air-water interface, which is basically this level. If you use the formula for apparent depth, okay, the formula is apparent depth is equal to actual depth into mu2 by mu1. Mu2 is the medium in which the observer is present. Mu1 is the medium in which the object is present. Okay, mu1 incident rays. No, incident rays will come from object only. So the real depth from the interface is 15 centimeters multiplied with observer is in air. Object is in water. Water refractive index is 4/3. So the apparent depth will be 3/4 of 15. 15 3 is 45. 45 divided by 4 is 11.25 centimeters. That is where the image appears to be. And that 11.25 is from the interface. Remember that. This distance is 11.25. So from the observer, now this is 20, this is 40. So this will be 20 plus 11.25. The answer is 31.25 centimeters. Is it clear? Rishi, did you understand?
Yes, sir.
Where did you get stuck? What were you trying to do?
Sir, I got 11.25. Then after that,
Okay. Remember, real depths, apparent depths, or just like object distances and image distances, they are measured from the interface, not from somewhere else. Okay. Next. Let's consider a similar situation, not exactly the same. Suppose there is a fish tank. Assume this fish is looking at something above water. Okay, maybe there's a, okay, let's consider some object here. It's exactly vertically above the fish. The object which the fish is looking at, let's say it is at a height of, how much shall we take? 50 centimeters or okay, 60 centimeters above the water level. Okay, this 60 is not from the eye of the fish. From the water level, it is 60 centimeters. Find out how high it appears to be above the water level. Water refractive index is 4/3. So actual height above water is 60 centimeters. You have to find out apparent height this time instead of apparent depth. Any answer?
sir, can you repeat the question?
There's an object somewhere in air at a height of, not somewhere, there's an object in air at a height of 60 centimeters above the water level. So the actual height is 60 centimeters. You need to find out how high it appears to be as seen by the fish.
Sir, is it 80? Not sure.
We'll see. Pradyun, any answer? Okay, fine. Rishi, how did you get 80?
Sir, I put x into 4
Correct.
by 3 by, no, 4 by 3 by, no, it's 1 by 4 by 3 is equal to 60. Done.
Okay, fine, fine. So you can imagine rays from the object. Now see, the fish is the observer, okay? And it's inside water. The object is in air. Now rays from the object have to reach the observer. So one ray travels straight like this. Other rays, if you imagine, just visualize one more ray incident this way. Now the light is traveling from rarer medium air into denser medium water. When it travels from rarer to denser, it has to bend towards the normal. So instead of traveling straight along this line, the ray bends towards the normal somewhat like this. So it appears to be coming from somewhere above. Okay. The common point for these two rays is somewhere here. So this is the object. This is the image now. Image appears farther than the object. And we know that when we had written that here, no? When mu2 is more than mu1, means incident rays are in rarer medium, refracted rays are in denser medium. Then image is farther than the object from the interface. So that is what is happening here. So the object appears to be higher than it actually is. But the formula is the same. You can use the apparent depth formula itself. Or don't even call it depth. We know x is equal to d into mu2 by mu1. Where x is the apparent distance and capital D is the actual distance. You don't have to call it depth or height, just call it distance. Okay. The actual distance of the object from interface is 60. Mu2 is the medium in which refracted rays are traveling. That is water now. 4 by 3. Mu1 is the medium in which incident rays are traveling. That is air. 1. That's all. 60 by 3 is 20. 24 is 80 centimeters. So that object which the fish is looking at appears to be at 80 centimeters above the water. Pradhin, is this clear? Okay. Fine, we'll stop it here for today. So what all have we discussed? First, we looked at some images where refraction of light is seen. Okay, some pictures where refraction of light is observed. And then we discussed how to find out the angle by which the light ray bends by using Snell's law. Light bends because of the difference in speed with which light travels in the two media. And based on that difference, there is a certain extent to which it bends. And that is given by Snell's law. Mu1 sin I is equal to mu2 sin R. When it travels from rarer to denser medium, it bends towards the normal. Denser to rarer medium, light ray bends away from the normal. Okay. Then applying Snell's law, we derived a relation between object distance and image distance from a spherical refracting surface. You can apply this result to a flat refracting surface also by assuming radius as infinity. Okay. But remember, the formula is valid only for paraxial rays. Okay. We got the formula. We used it for a flat surface. We even derived the formula for apparent depth. We applied it in case of apparent height also. Okay. So next class, which will be on Thursday, we will discuss more applications of this formula. How to locate the image. If possible, we'll try to find out the magnification also. And based on this formula itself, we derive something called the lens formula. Okay, lens formula, lens maker formula and all. Okay. Thank you all. We'll continue in the next class.